Hey guys, the purpose of this video is to evaluate the brand new power meter which I have received. This is a I'm going to open this box as we speak. This is a RADOM 2 kilowatt CW RF power meter and reflectometer. Essentially, this device allows you to measure RF power, both forward and reflected, between 400 and 500 megahertz. So in this box, let's see what we have in the box. I just received this device and I'm going to open it up. The device appears to be well packaged and has a bubble wrap bag. And it looks like this. Okay. So basically, let's see what we have. So on two sides we have end connectors and female. On the top we have a 4-line LCD, 20 characters by 4 line. We have an adjustment knob, and it states here that the device operates between 400 and 500 megahertz up to 2000 watts CW with insertion loss less than or typical 0.02 dB. The impedance is 50 ohms. On the side we have a USB port, reset button and mode button, and then on the bottom and on the top we don't see anything. So the device is relatively heavy, I would say about 2.5–3 pounds maybe. It appears to be machined aluminum. And let's see what else we have in the box. There's a power meter, the AC adapter. Operates between 100 and 200 volts, 5 volts VDC, 100 milliamps with a mini USB port. Alright, so before we get started, let me tell you a couple of things about myself. I am an electrical engineer. I've been in this business for about 10 years. I've been doing all sorts of different things, digital electronics, RF, audio, and so on. And my latest project is a high power amplifier up to 1000 watts in 70 centimeter band between 400 and 500 megahertz. And unfortunately I haven't been able to find a cost-effective solution to do the power measurement until I ran across an eBay item. This particular item here, manufactured by RADOM Corporation. And I looked around. I was trying to find a video on YouTube to see how this device operates. And unfortunately I wasn't able to find one. It appears that this is a relatively new product, and that's the reason I'm doing this review. So let me first show you some of my equipment that I got here in the lab. Up here on the top I have an Agilent RF power meter which measures power up to 20 dBm, which means up to basically 100 milliwatts. This RF power meter, state-of-the-art RF power meter, is connected to two RF sensors. Without these sensors you really can't do much. Below that I have an oscilloscope, which I won't be using in this video, but I will be using this device, which is the RF signal generator, up to 1 gigahertz, output frequency up to 10 dBms, which is 10 milliwatts basically. And then here on the side I have a network analyzer, a 4-port Agilent network analyzer, which I basically will use to evaluate this device and see if the manufacturer published data is correct. Let's see, how correct the data is. Okay, so the goal of this experiment is to do a comparison between this new RF power meter, which I have received today, and state-of-the-art Agilent power meter through a RF attenuator. And by the way, when I position my setup here, you'll see that I have a high power attenuator. However, my attenuator is limited to 500 watts power, so I'll be testing this device up to 350 watts and see how these two compare. So without any further delay, I'm going to power this thing up and see how it operates. See what we get. Okay, powered up, really nice. So let's see, what do we have here? So it appears that we have only two menus that are user accessible, and it looks like on the first page, in the first menu, we have something what looks like forward power. Units are dBm, so it's basically logarithmic scale relative to 1 milliwatt. There's a reverse power. It automatically calculates VSWR, and there's frequency adjustment, so you can basically select your frequency. Here it appears that would most accurately do your measurement. Okay, on the second page, let's see what we have. So it seems like we have some sort of averaging, RF direction, RF units, and I would say selection between VSWR and diff, maybe difference or something. Alright, so I wasn't able to find the user manual. It hasn't arrived in the box, but I called the manufacturer and inquired about this device, and they explained to me that there are a number of things that you can select here and adjust with this adjustment knob. It basically, when you rotate it, it just goes continuously either left or right. But if you press and hold this button, for example on the first screen, for about 4 or 5 seconds, it enters this edit mode. So when you see this blinking cursor, what that means is that you're in edit mode. So this is how you adjust the frequency for the most accurate measurement. Okay. Another thing that's interesting here is that the VSWR value here is negative, and as most of you know, VSWR, the lowest you can be is 1.0. So I inquired about it, and they basically explained to me that this is normal when there is no RF power connected to it, because the meter is basically calculating VSWR over noise. Okay. Another thing that it could mean that you have your RF power input connected on the wrong side. Okay. So to exit the adjustment mode, again you just press and hold the adjustment knob, and there you go. You just exited the adjustment mode. On the second page, again, you press and hold, and you can adjust the averaging factor from basically 1 to 32. So according to the manufacturer, what they have explained to me is basically the meter performs up to 32 measurements and then averages the result. They suggested anything between 5 and 10 should be sufficient for typical measurement, so I'll just leave it at 10. Now to go to the next line, you just press it once without holding. You just press it and let it go. It skips to the next line. Again, if you want to go to the third line, to the fourth line, and it comes back to the first line. So on the second line, according to them, this is how you adjust which side is the input side. So here's port number 1, here's port number 2, and then you can have your direction from 1 to 2 or from 2 to 1, depending upon your particular setup. And this is mostly mechanical constraint. Basically, if your power comes in from the left to right, and then you can select 1 to 2, and that's how I'm going to test it. Then the third line is basically allows you to select between watts and dBms. So this, the main display, if you remember earlier, was showing dBms. When you select watts, it will show the power in watts. And then on the fourth line, basically what this allows you to do is select either VSWR display on the first menu, in the first menu, or the difference between forward and reflected, meaning basically that you can see actual power absorbed by the load by doing that. So let's just leave it as this. Let's select watts and select forward minus reflected, and exit the edit menu, go back to the first page. So now, as you can see, it shows watts, and it also shows forward minus reflected. Earlier it said VSWR. Alright, so the next thing I'm going to do is I'm going to verify some of these numbers in this datasheet that came with the device. Basically what I'm going to do is I'm going to verify that the insertion loss of negative 0.03 dB typical between 400 and 500 megahertz is indeed correct, and I'm also going to check this return loss. Okay. So to do that, I'm going to use an instrument called network analyzer. This particular device is an Agilent E5070B, as in boy. The operating frequency is between 300 kilohertz and 3 gigahertz, but I have it set up between 350 megahertz and 550 megahertz. Okay. So first thing I'm going to do is I'm going to first verify that my this is, by the way, this is reflection, it's S11. I'm going to verify that the device has been calibrated correctly. So with a 50 ohm calibration load, I'm reading very good return loss. Typical, it's negative 53 dB or better. So the question is, when I connect this cable to this instrument with a 50 ohm calibration load in the output, what is the return loss? Okay, so I have 3 markers first marker sits at 400 megahertz, second one is 450 megahertz, and the third one is 500 megahertz. It looks like the 500 megahertz is the worst case scenario, and it sits at negative 26.5 dB. The manufacturer's datasheet states that 26 dB is basically typical for 500 megahertz, and 27.8 dB for 450 megahertz. Alright, I'm going to do the same for going backwards. I'm going to swap these around. So for this test, we don't really care, what the display is showing. This has nothing to do with the display. This is just basically looking through into this through line. Okay. So again, pumping the power this way as opposed to that way, and having the load on this side. It looks like again 500 megahertz is the worst case condition, and negative 26.5 is the reflection. Okay, so basically there is no difference whether the power goes this way or that way from the reflection standpoint. So the next thing I'm going to do, I'm going to switch my measurement to S21, which is basically a transmission, in order to measure the insertion loss of this device. And this is important because in order to have a very good RF power meter, you basically have to have an extremely low insertion loss. So let's see if what this manufacturer states. Insertion loss of typical 0.03 dB, which by the way is extremely low for this kind of instrument. Let's see if that really measures up. So I'm going to inject the power into port 2 and measure what comes out of port 1. Okay. So S21 scale, auto scale, didn't auto scale correctly. Let's set my scale to 1 dB per division. Okay. So this is an extremely low insertion loss, so it's jumping a little bit. But of course, before I even get anything measured, I should probably verify that my instrument is calibrated, that it's still calibrated. By the way, I had it calibrated earlier, but it's always good to check. So this is just a typical true cal, and the insertion loss, it says 0.003. Okay. So the power will be ejected into port 1 for this test, and I'm going to measure it on port 2 on this power meter. Alright, so it looks like the line is very flat. It's really hard to tell. Maybe if we zoom in a little bit and say scale per division 0.1 dB. So you can see that this is in milli dBs here, and it says that the insertion loss is 0.04 dB. If we add some averaging, maybe it's going to improve between 0.03 and 0.04 dB. And the manufacturer says it's typical 0.03 and up to 0.05 dB. That's the insertion loss. Alright guys, so now that we've finally confirmed that the manufacturer's data sheet is indeed correct, let's see how this device compares under some load. Okay, so basically what we're going to compare the measurement of this RF power meter with state-of-the-art Agilent RF power meter through an RF load. So basically the RF power goes to this cable into the RF power meter through 50 dB attenuator, rated it up to 500 watts, and then in the end I have the sensor. So the power meter has been calibrated and the attenuation has been entered into the device, so we're going to be able to directly compare these two instruments during the measurement. Okay, so let's first say something about my setup. So over here on the right I have the RF signal generator set to 450 megahertz frequency. The RF power is currently off, and then the RF signal generator is connected to RF preamplifier that outputs up to 10 watts, and the signal goes into this RF power module, which is basically the module that I'm trying to test here. So this device here is capable of outputting up to 1000 watts of RF power, CW RF power, if of course designed correctly. And I'm trying to adjust this device. Unfortunately I have some limitations here. First of all, my DC power source can only deliver 1 kilowatt of DC, which is insufficient for this RF power amplifier, because this RF power amplifier requires as much as 2 kilowatts of DC in order to produce 1 kilowatt of RF. So let's give it a try. Alrighty. So I'm going to turn the RF signal generator on, and you can immediately see that we have some RF power going into the load. So roughly 28.6 dBms is injected into this port right here, port 1 of the RF power meter, and goes into the load. Okay. This load could be an RF load, or it could be an antenna. It could be some other load, such as some RF plasma device, but in this case it's just an attenuator up to 500 watts with total attenuation of 49.5 dB. So as we can see here, 28.6 dBm is measured by the sensor, and the RF power meter here shows exactly that, 28.6 dBm. So what I'm going to do next, I'm going to increase the RF excitation of the signal generator and see how the two compare. I'm going to increase it slowly, 1 dB at a time on the RF signal generator, and we can immediately see some effect. So 40 dBm, 40.5 dBm is roughly just over 10 watts of RF, and we can see that it reads 40.55 dBm on the RF power meter, the state-of-the-art Agilent RF power meter. And by the way, this is RA4050 Agilent power meter, and the sensor is Agilent RA4050-2000 average RF power meter. So the two, you can see, definitely compare really well, really good. So as we keep increasing the power, let's see how they compare at roughly 100 watts. So this is just over 100 watts, 50.86, 50 dBms basically is 100 watts. And here we're reading 50.8, and here we're reading 50.9. So very close, very close. And then if you continue going, as much as my DC source is going to allow, which is 20 amps. We end at 55, almost 55 dBm, and this device is reading exactly that, 54.96, 54.86. Okay, so let's see how these compare under some other conditions. The next thing I'm going to do, I'm going to switch to watts. So press and hold for 5 seconds, enter edit mode, press twice more to get to dBm, RF units, change that to watts, press and hold to exit edit mode, and go back to screen number 1. Here we can also do that, we can switch to watts, and right now we're reading 697 milliwatts, and here we're reading 690 milliwatts. So let's see how they measure at very low input power, say 187 milliwatts. So we're reading 187 milliwatts here, 191 milliwatts here, so very close. So next I'm going to increase the power, go up to say 10 watts. 10 watts. So here we're reading 10.1, here we're reading 10.5. So at higher power, it's off by only 0.4 watts. We continue going. 114 watts here. Here we're reading about 1.16, 116 watts. 113 here, 115. So about 2 watts off, which is within the 3% level, and we can calculate that if needed. So let's keep going all the way up to as much as my DC source is going to allow me, which is 20 amps. So here we're reading 323 watts, and here we're reading 323 watts, so exactly the same. So overall it looks like the power meter is pretty accurate. So going down to lower power, let's say 10 watts. Let's see what happens if we change the frequency, measurement frequency of this device, the calibration frequency of the device, to the relative measurement, or the accuracy. So I'm going to change that to 425 megahertz and see how they compare. Alright, so immediately you can see that this guy measures about 8.96 watts and this guy measures 10.45. So it looks like if you're not exactly on the frequency, that the accuracy falls off quite significantly. So I would say it's pretty important to have that frequency as close as possible to your expected operating frequency, which in this case is 450 megahertz. And then do your work. So 9.23, 9.64. So pretty close. Alright, so looking closely into this device, let's see how the rest of these features could potentially be used. So here on the first screen we have direct readout of the forward and reflected power. So it appears that there are two separate sensors within this device. According to the data sheet, it says that it has a dual power sensor, one which measures the forward power and the other one which measures the reverse power. And what that allows you to do, or to see, is the VSWR, or voltage standing wave ratio. So basically your load could be just about anything. It could be an open circuit, it could be a short circuit, it could be an antenna, and you can see exactly what your VSWR is. So it looks like in my case here I have a VSWR of 1.1, which is pretty good. most of the power is being dumped into the load. We can also change this to a different readout, that particular field. We can change that to forward minus reverse or reflected and see how that looks like. So it looks like the 10 watts comes in, and just below that we see how much power is actually lost, how much power is reflected, to be more precise. It looks like only 350 milliwatt or 35 milliwatts is reflected off the load, and here we can see how much power is actually deposited or dumped into the load. So roughly 9.94 watts is dumped into the load. Another thing we can do here, we can average this a little more. Let's say we go up to maximum. And you get a much more stable readout. So it looks like 9.98, 9.92, so roughly 35 milliwatts is reflected. Another thing we can do here, we can change direction and pretend that we're pushing power from port 2 to port 1 and see how that affects the reading. So now what happened is you can see that these two switched positions. So now it says reflected power 9.94, but that's only because we're actually pushing the power in this way, but we're measuring this way. So this is all good, and then you can see that it's actually showing negative power, but that's only because we have selected, like I said, wrong direction. And in some cases that may be useful. Again, if you change this to VSWR and go back to the direction, see how that affects the VSWR reading. So in this case, since we're pushing the power from the wrong direction, or we selected the wrong direction, you can see the VSWR is negative, and that's only because we're pushing it from the wrong direction. But the number, absolute value of the number, is what really matters. We go back and switch this to 1 to 2. We're injecting the power from port 1. Now we can see positive numbers, and everything looks good. The last thing I want to do is compare, from the cost standpoint, this state-of-the-art instrument with this instrument. So first of all, this instrument here is the Agilent RA4050-2000. It's an extremely good instrument. However, the only limitation is that it can only measure power up to 20 dBms, which is 100 milliwatts. When you're building an RF amplifier, such as the one that I have in front of me, you need either an attenuator plus this instrument, or something like this. Okay, so this instrument, I just printed out some cost. The cost of this instrument is about $8,300, brand new. It's a dual port. This is without the sensor, and then you need a sensor, and each sensor is $2,400. So these two combined, we're talking roughly just over $10,000 for these two units, plus the cost of the high power attenuator in order to do a measurement. This, on the other hand, and that's the major reason why I had purchased this instrument, I paid only $2,500 on eBay. It was a straightforward purchase. That was the most efficient way for me to do it. And like I say, it was only $2,500 and allows me to measure power, the CW power, up to 2 kilowatts according to the data sheet, and everything is included. It is important to note, of course, that you need to have a load connected to this device before you can do your measurement. It has to be either an RF load, typical resistive load, or an antenna or some other type of load that you may be using. So from my standpoint, this was a very good investment, at least for my needs, and I'm going to be able to now just buy a relatively cheap RF load, comparing to all this setup, this plus the sensor plus an attenuator, high power attenuator, which by the way is extremely expensive in order to do my measurements. So I should be able to do everything up to 2 kilowatts between 400 megahertz and 500 megahertz, and hopefully it'll work out for me. So thank you all for watching. If you have any questions, comments, please let me know. Put a comment down here below and I'll try to answer it. I hope the video was useful. I hope that some of you will make some comments and maybe make some suggestions what else I could do with it, and then we can go from there. Thank you very much for watching, and see you later.